This video gives a brief introduction to the methods and results in this paper. To operate properly, the electricity system needs to keep its frequency, a measure of supply and demand balance, at close to 50 Hz. This frequency control has traditionally been performed by flexible generators, such as gas plants, that respond to fluctuations in the supply-demand balance. Generation needs to increase, or demand needs to decrease, when the frequency drops below 50 Hz, and vice versa when the frequency rises. More renewable power makes generation more volatile and less predictable, so balancing the system becomes more difficult. In future, appliances such as fridges and air conditioners may be able to play a role. Appliances like fridges work by switching on when they get too hot, staying on until they become cool enough, and switching off. The operation is simple, and unlike your television, no one minds when their fridge is on or off, so long as their food stays fresh. This simple example shows how 50 fridges might operate normally, heating and cooling between their temperature set points. The simulation has been sped up, as normally one cycle would take around an hour. Fridges can be adapted to monitor the system frequency and change their temperature set points to advance or delay cooling. Individually, each fridge would act very similarly to normal, but as a large group they can make a significant difference. For example, here we let the temperature set points of a group of identical fridges vary in a simple deterministic way based on the frequency shown on the right. When there is a large frequency incident, such as this one here, the fridges clearly respond, but they are likely to cluster and eventually synchronize switching on and off, which can lead to bigger frequency problems. These issues don't occur if the fridge conditions are sufficiently heterogeneous, because their differences allow them to desynchronize. Fridge conditions are naturally heterogeneous because, for example, room temperatures, cooling rates, and temperature preferences vary between fridges and households. The goal of this paper is to determine how much heterogeneity is required to prevent the synchronization issues found in our previous paper. To determine the minimum heterogeneity requirements, we introduce a standard deviation factor, or SDF, which allows us to increase the standard deviation for multiple normally distributed parameters simultaneously on different scales for different simulations. An identical population has zero standard deviation, for example, room temperatures all at 20 degrees. We increase the SDF by powers of 10 due to the very low levels of heterogeneity we find we require to prevent synchronization issues. Our simulations take system input data for Great Britain, such as demand and historic system frequency, and a model for how the original frequency response providers acted and would have acted if the fridges had been providing frequency control. We simulate the system every second for 10 days, 36 times over 1 year, to see how 1 million fridges would have behaved and how the other response providers would have acted. The key question is whether the fridges reduce the amount of response needed from everyone else, which we call response savings, or whether they do more harm than good and require more response due to synchronization issues. For each of the 36 simulation runs, we calculate the cumulative response savings over 10 days, i.e. the reduction in response needed from the original providers in the presence of the fridges. When the fridge conditions are identical, many of the simulations result in negative savings, more harm than good due to synchronization. When the standard deviation of the distributions is very tiny, there are still synchronization issues and negative savings. Once the standard deviation factor reaches about 10 to the minus 2, none of the simulations come close to showing synchronization issues. We show in the paper that this is a very tiny amount of parameter heterogeneity, well within what might be expected. For example, almost all room temperatures would be within 0.04 degrees C of the mean. The first contribution of this paper is the study introduced here, determining the minimum heterogeneity required to prevent synchronization, which I find is well within what could be expected in a population. I also determine the relationship between the number of fridges providing frequency response and the amount of response that they can deliver. Finally, I investigate varying the sensitivity of the fridges to the system frequency and the impact on both the fridge temperatures and the total response they can provide.